time. Also, something that you'll notice, I had some people that were working on kind of the review, going through some practice. I did post the answer key to it. Now, my answer keys from what we've used in previous years where we got through the full curriculum versus this year we had to cut certain things out. So my numbers may not match exactly, but the questions are on there. So you kind of match up the questions. The review is still arranged by the same unit order. So you can kind of follow along that way. That's kind of a way to go through and check your answers. If you're not getting something, that's where we can talk a little bit more individually to kind of figure out what you're missing and how we can fix that. So the recording starts, we'll go ahead and go. So today we're going to go through bonding and reactions. So with bonding, we first started looking at the different types of bonds that we have and their different properties. So remember, we have three main types of bonds. That's the ionic, metallic, and covalent bonds. Remember, ionic is between a metal and a nonmetal. So those like cations and anions. Metallic is just going to be metals only. That could include those alloys, which are the mixtures, things like brass, bronze, steel. That could be included in metallic. And then covalent, remember, was also referred to as molecular. That's between nonmetals only. So you could look at a formula, look and see, does it have metals? Does it have nonmetals? Does it have both? And that's how you can kind of figure out what type of reaction it is. Looking a little bit more in depth at each one. So let's kind of go through ionic. So remember, ionic was the metal and nonmetal, or the cation and anion. So with ionic compounds, there's a transfer of electrons. So that transfer of electrons is what causes that charge. Because remember, the cations lose electrons. Well, they don't just float off into space. The anion picks them up. So it truly transfers from one substance to another. With ionic substances, they tend to be solid at room temperature as like crystals, and they're very brittle. So if you were to like hit them with a hammer, they would shatter. They're not going to bend and mold into different shapes. So think of like table salt. Those little individual tiny crystals are what we're talking about. With ionic substances, they tend to have high melting points and boiling points, which is why they're solid at room temperature. We also talked about ionic when we did reactions and we looked at solubility rules. These tend to be mostly soluble in water. There are some things that are not soluble in water, but that's where we had to use those solubility rules in our chemical reactions unit. But a lot of ionic compounds will dissolve in water to some extent. And then the last thing we talked about property-wise about different types of bonds were their conductivity. So for ionic compounds, they will conduct electricity or heat if they're a liquid or in aqueous solution. So if they're melted or dissolved, they can conduct electricity because those ions are able to move around. But they will not conduct electricity as a solid. And we're not going to be able to get these hot enough to change them into a gas. So we don't tend to worry about that. So that's where if you poured table salt out on the table and hooked a battery up to it, absolutely nothing would happen. But as soon as you dissolve it in water, it will conduct electricity. That's why, like in the summer, if you're out at the pool and you hear thunder, everyone has to get out because the water doesn't conduct electricity, but it's all the chlorine and the sweat and the sunscreen and the salt and everything that's in the water that conducts the electricity. All right. Let's switch over to metallic. So like I said, these are just metals or those alloys, which are the mixtures with different metal ions. These are going to be represented as a sea of mobile electrons. So these aren't actual bonds, they're just kind of attractions. But what you have is you have all the nuclei in the substance and all of their electron clouds are overlapping. Well, those electrons can travel from one electron cloud to another and literally hop from one atom to the next. So since those electrons are able to move around and the atoms aren't locked in place, they can move around. That kind of determines some of those special properties of metals. So metals do tend to also be solid at room temperature, with the exception of mercury. But these tend to be fairly flexible, depending on the metal. So a lot of times we'll refer to metals as being malleable or ductile. So that's where if something is malleable, it can be beaten into sheets. So that's where they can make aluminum foil, they can make sheet metal, things like that, where they literally hammer it down into a thin sheet. Ductile is where something can be drawn into wire. So like a lot of the wiring in our houses and stuff is probably copper based. They can literally take copper, pull it out into those thin wires, and then coat it with plastic. So it's not going to pull apart and break like something softer would. Since these are solids at room temperature, they also tend to have very high melting points and boiling points. Metals are not soluble in water. So you're not going to be able to put like aluminum foil in water and have it completely dissolve and go away. And in terms of conductivity, these always conduct. So these are the only ones that will conduct as a solid. And the reason it conducts is because of those free electrons. Since the electrons are free to move around, the electricity or heat is free to move around. And then scooching over to covalent. So covalent or metallic or molecular, excuse me, was between nonmetals and nonmetals. So we're not dealing with charges or anything like that. So what's happening here is we are sharing electrons. So that's where we form those bonds that have two electrons that belong to both atoms. These tend to be, most of them are going to be gases at room temperature or liquids at room temperature. And a lot of times that may depend on how heavy the substance is. These tend to have low melting points and boiling points, which is why they're liquids or gas at room temperature. In terms of solubility, these are going to be soluble if they're polar. So I remember we kind of talked about that like dissolves like, where polar substances dissolve polar things, nonpolar things dissolve nonpolar things. So these are soluble in water, but only if they're polar, only if they're going to have attractions between the covalent molecule particles and the particles in water. And these are never going to conduct electricity. So like I said, pure water doesn't conduct electricity, but as soon as there's any ions or minerals or anything in there, it will. But it's not the water that's conducting, it's all the ions and stuff in the water that's conducting. So like I said, this is something that you'll probably see, and it's very likely that it might say, okay, which of the following is a property of KCl? And you'd have to say, okay, KCl, potassium's a metal, chlorine's a nonmetal, so this is ionic. Which of the properties listed is an ionic property? So that's kind of how these may be approached. All right, then we went into with bonding. We also spent a good time on the actual dot structures. Most dot structures are going to be covalent. That's what we tend to deal with the most. Kind of remember general rules for drawing dot structures. You want to count the number of valence electrons. So remember, valence electrons you can find based off of what column or what group that element's in on the periodic table. Remember on our periodic tables, up at the top, it has like in Roman numerals 1A, 3A, 5A. The Roman numeral is how many valence electrons that substance has, with the exception of helium. So that's kind of how you can tell valence electrons. So we're going to add up the total number of valence electrons in our structure. Whatever is listed first goes in the middle, with the exception of hydrogen. We're going to attach all of our outer atoms to the center atom using bonds. And remember that bond is equal to 2 of your electrons. Then we look at our outer atoms and we want to fill their octets. So remember, everything wants to have 8 valence electrons, except for hydrogen and helium that only want 2. Once we've filled all the outer atoms, if we have leftover electrons, they're going to get dumped on the center atom. And then we want to make sure that everything does have a full octet. So if for some reason something does not have a full octet, a lot of times that may happen with our center atom. That's when we can steal a pair of electrons and make a double bond or even a triple bond if needed. So for example, kind of a common one that we dealt with was ammonia, the NH3. So if we were kind of walk through the steps with this one, finding valence electrons, nitrogen has 5 valence electrons, plus we have 3 hydrogens, and each hydrogen has 1 valence electron because they're in that group 1. So this is a structure with a total of 8 valence electrons. So we said whatever's listed first goes in the middle unless it's hydrogen. So we have nitrogen in the middle with our 3 hydrogens kind of hanging out. We said we connect everything to the center atom using a bond. So that's 2, 4, 6 electrons. All of our hydrogens are full because once hydrogen has 2 electrons, it's done. So our 2 leftovers are going to go on the center. And right now, everything does have its full octet because all 3 hydrogens have 2 electrons and nitrogen has a total of 8. So that's what our dot structure for ammonia would look like. One where we might have to rearrange some. Let's look at SO2. So finding valence electrons for this, sulfur is number 16 if you need help finding it. It's underneath oxygen, so it's in group 6A, so it has 6 valence electrons. Add to that, we have 2 oxygens. Oxygen is also in group 6A, so it has 6 valence electrons. So that's a total of 18 valence electrons in this structure. Sulfur, since it's listed first, is going to go in the middle. Our 2 oxygens are kind of going to hang out on the outside. We said we connect everything to the center. So that's 2, 4. Fill our outer atoms. So one of these oxygens, whichever one you pick, currently has 2 electrons. So to have a full octet, it needs 6 more. So that was 4 that we've used. That's 5, 6, 7, 8, 9, 10. The other oxygen needs the same thing because it has the same number of electrons. So that was 10, 11, 12, 13, 14, 15, 16. So both of our outer atoms are full, but we have 2 electrons left. So any leftovers get dumped on the middle. So we're out of electrons, but we said we need to make sure everything has a full octet. Both oxygens have 8 right now, but sulfur only has 6. So that's where we can steal a pair from one of the oxygens and make it a bonded pair. So add that double bond, because then oxygen still has its 8, but we moved them over to where sulfur also has 8. And remember, it doesn't matter which side you put that double bond on, because this is where we can have resonance structures, where if you put the double bond on the left, it's correct. If you put the double bond on the right, it's also correct. All right. With the dot structures, we then started looking at the shapes and polarity of those different structures. So we did that using VSEPR. So VSEPR is our valence shell electron pair repulsion. So remember, those outer electrons in the valence shell want to be as far apart as possible. So they will arrange themselves to reduce the amount of repulsions to be as far apart as they can. So we had 5 different shapes and 3 different geometries. And I'm kind of going to sketch one of these so you can see what it looks like. So shapes, we had linear was our first one. Remember, linear is where there's 2 atoms attached to the center and then no dots on the center atom. So they will truly be straight across from one another. If something is bent, there were 2 ways that you would see something that was bent, but bent had 2 atoms attached to the center, but then it also had electron pairs on the center atom. Sometimes you'll see it with 1 electron pair, sometimes you'll see it with 2 electron pairs. Then there was the trigonal planar. So remember, the prefix of tri means 3. So this is where we had 3 atoms attached to the center atom. And the center was plane, which is the planar. So there's no dots on the center atom. We then have the trigonal pyramids. Remember, tri means 3, so there are 3 atoms attached. But there is an electron pair on that center atom. And then tetrahedral, remember, tetra means 4. So this is where we had 4 atoms attached to the center atom. So looking at these in terms of polarity. So remember, polarity was related to if there was a difference in electronegativity, but the different shapes can allow those kind of polar bonds to cancel out and be nonpolar. So with the shapes that don't have dots on the center are going to tend to be nonpolar as long as all of those outer atoms are the same. So like if one of the outer atoms is a hydrogen and the other one's nitrogen, they're not equal strength. So even if that's something that's linear, it would still be polar. But kind of the general rule is if there are not dots on the center atom, it's nonpolar. If there are dots on the center atom, it's going to be polar because those forces can't cancel out. With VSEPR, we also looked at those molecular geometries. So this looked at how many total electron groups were around the center atom. So how many atoms are on the center atom and how many unshared electron pairs around the center atom. So this is how many total groups were around the center. So I'll kind of show you, let me switch colors so you can see this more clearly. Let me do red. So if we were looking at this bent shape right here, it has 2 atoms attached to the center atom and an electron pair on the center atom. So this would have 3 total groups on the center. So this would be trigonal planar whenever we're looking at its geometry. Whenever there are not dots on the center atom, the shape and geometry are the same. But like if we're looking at this trigonal pyramid with 3 atoms attached and an electron pair, there's 4 total groups around the center. So that would be tetrahedral. There's also a form of bent with 2 electron pairs on the center that is tetrahedral, like water. So it's just kind of remembering how you look at these individual pieces. All right, and I already talked about polarity a little bit, but polarity is whenever you have that difference in electronegativities. So you have one substance or one atom that's stronger than the other, so it's kind of hogging the electrons. We also talked about those intermolecular forces that occur between molecules. These, remember, are weaker than actual bonds. They're simply attractions or forces. So the 3 that we had were hydrogen bonding. This can occur whenever we said hydrogen is fun, F-O-N. So whenever hydrogen is attached to one of those very electronegative elements, like fluorine, oxygen, or nitrogen, it can form hydrogen bonding, where that hydrogen is going to be attracted to another molecule's electronegative element. So that we said happens between water. That was one of the things we looked at. So like water, that oxygen is very electronegative. So this hydrogen is going to be attracted to another water molecule. So a lot of times, remember, these are seen as like dotted lines instead of bold lines. Just saying that there's an attraction here where they're kind of being pulled together. I remember the hydrogen bonding is the strongest of those intermolecular forces. Then we have dipole interactions. So this is where we have 2 polar things that are attracted to one another. So you have that as opposite poles, that positive end and negative end, that are attracted to each other like magnets. That one is weaker than hydrogen bonds, simply because it's a lower electronegativity difference. But remember, hydrogen bonding is just a very, very strong dipole because those substances are more polar. And then we have dispersion forces, which are the weakest of these. These were the ones where they're in everything, but they're kind of the primary force in those nonpolar substances. So that's where for a split second, you have that unequal distribution of electrons. So for a split second, you have what we refer to as an induced dipole, where there's more of a negative charge on one side of the atom and more of a positive charge on the other side of the atom. So then it influences the atoms in the surrounding area. But like I said, it's a split second. It's going to rearrange and go back to normal. So it would just be, if you were to take like a snapshot of that moment in time, it would be out of whack where there's more electrons in one area than another. And then you take a snapshot a second later and it's completely back to normal. So that's a very temporary force, which is why it's very weak. All right, and then looking at chemical reactions. Remember, chemical reactions is where you have a ton of stuff on your reference sheets as like your cheat sheet. It gives you a lot of information. So remember, chemical reactions, your starting products are your starting materials are your reactants. Your final materials are your products. So generally, your reactants are on the left side of the yield arrow. The products are on the right side of the yield arrow. With reactions, we have to deal with the conservation of mass or conservation of matter. So this is where we had to balance equations. So we had to make sure that we had the same number of atoms on each side of the equation. So if we had 1 nitrogen on one side and 5 on the other side, we would have to multiply that substance by 5 so that they could be equal. So that's where we could add in coefficients to change the number. There are 5 main reaction types. These are the ones that are on your reference sheet. So this includes your solubility rules. So this is actually on page 6 of your reference sheet. It has solubility rules and then types of reactions, and it gives you those kind of general patterns for those. So I'm going to go over the general patterns. I'm going to have to switch back to blue. I can't write in red. It makes me feel like it's bleeding. All right. So looking at the types of reactions, our first one was a synthesis reaction, which can also be referred to as a combination reaction. The general pattern it gives you for that is that A plus B produces AB. So you generally have 2 elements that combine to form a product. It can be 2 compounds that combine to form a product. So the thing that you're looking for is that there's only going to be 1 product in a combination reaction. So whether it's 2 elements or 2 compounds or an element and a compound, if there is 1 product, it's going to be synthesis. Then we have decomposition reactions. These are the opposite of synthesis. So this is where we have a compound and we are breaking it up into 2 or more substances. So the general form is that AB produces A plus B. Now, this is for like if it's a binary compound that only has 2 elements. If it has a polyatomic and stuff, there are special rules on your reference sheet to tell you how it splits apart. So the kind of key factor for decomposition is it only has 1 reactant. And remember, we didn't predict the products of these. We only identified these. So this would be, it might give you a reaction and say what reaction type is the following. And you have to look and see what pattern does it follow, what type of reaction it is. Or it could ask you which of the following is a decomposition reaction. Look at the choices, see which one only has 1 reactant. Then we had our ones that we predicted products for. So this was included in our chemical reactions lab too. So we had single replacement. This was the one that had the general form of A plus BC produces B plus AC. So you're going to have an element in a compound producing a new element in a compound. So generally you have whatever the substance is by itself is switching places with something in the compound. If it's a metal that's by itself, it's switching places with the metal in the compound. If it's a non-metal, it's switching places with the non-metal in the compound. And with single replacement, we had to look at the activity series to see if these would go. So remember, the activity series is on the back of your reference sheet next to your polyatomic list. There is an activity series for halogens, which are going to be your nonmetals. And then there's an activity series for metals. So remember, looking at the activity series, the lone element, so the one by itself, must be higher. If it is not, it will be no reaction. So if the element by itself is lower on that list, it's not going to make any products. It's just going to be no reaction. The one by itself has to be stronger, more active than the one in the compound to be able to push it out of the way and take its place. Single replacement is the only thing we use that activity series for. We didn't use it for any other type of reaction. Then we had double replacement. So these were the ones that had the general form of that AB plus CD. So we had two compounds, and the idea is for everybody to switch partners, so we make two new compounds. So we generally take the metals and switch places. So if that's the case, it forms AD plus CB. And that's what's given on your reference sheet. So you start with two compounds, end with two compounds. These always occur, but one thing that we add with double replacement is those solubility rules. So these are on your reference sheet up above the types of reactions. And remember, we look at these based off of the anion. So they're either going to be on the soluble list or the insoluble list. So if something is soluble, that means it dissolves in water. So it will be an aqueous solution. It'll be AQ. Whereas if it's insoluble, it does not dissolve in water. So that's where it will be a solid. So that would be like if we were looking at calcium nitrate or calcium carbonate. And we wanted to see what their state symbols were. So we would look up for calcium nitrate, we would look at the rule for nitrates. On our solubility rules, under the soluble side, it says nitrates are soluble and there are no exceptions. So this would be aqueous. Whereas calcium carbonate, carbonates are on the insoluble side. So it says carbonates are insoluble except for group 1 and ammonium. Well, calcium's in group 2, so it's not an exception. So this will be solid. And remember, exceptions are the opposite of the rule. So with carbonates, say that this was sodium carbonate. It does say that carbonates are insoluble except group 1. Sodium's in group 1, so this would be aqueous. So it would be an opposite of the rule if it's an exception. So hopefully you remember that. That wasn't too long ago. But remember, that needs to be included with double replacement. Remember, anytime it's a solid, anytime it's insoluble, it might be referred to as a precipitate. So anytime it's looking for the precipitate, it's looking for the solid. I forgot I had another button down there, but I wrote it, so it's okay. Okay. And then our last type of reaction were the combustion reactions. These are going to be those explosions. With combustion reactions, you have oxygen as a reactant. So there are there are reactions that could be listed as synthesis or combustion if oxygen's a reactant. But the ones that we focus on with combustion are the ones listed on your reference sheet. So these are going to be hydrocarbons. So hydrocarbons are all those organic things that have carbon and hydrogen in them. It's like CH4, C2H6, things like that. Those are going to be plus oxygen, produce carbon dioxide and water. Always. And that's what's listed on your reference sheet. These are the ones that tend to be difficult to balance, and you may have to go back and forth a little bit because you a lot of times can't have an odd number of oxygens on the product side. So you may have to double everything if you end up with kind of an odd number. All right, and that is where we're stopping today. So we made it through bonding and reactions. Tomorrow we're going to kind of walk through the mole stoichiometry, acid basis. One thing that you'll notice, so some of you guys have been working on the review that's posted. There is an answer key posted for the review. Now, I just kind of took pictures of my old review, so there might be some extra questions on there that are not on yours. The numbers also might be slightly different. So the question numbers might be slightly different, but they're all on there. They're still separated by unit. So that's kind of a way to go through. So that's where, as you're going through stuff, if you come across particular ones you have a question about, that's where we can kind of get together and talk that over. Most things should be kind of already graded and updated in Canvas. So if you notice something that's in Canvas that isn't graded, let me know. The only thing I have not gotten to in Canvas yet is the remediations for people that have done them. There may be some tests or quizzes in Flute that aren't graded yet. If you notice something that has been in there a while that isn't graded, please let me know so I can get it taken care of. So remember, second period exam is on Monday. So you guys have tomorrow, we'll finish up the kind of review stuff. You guys have Friday and then Monday. Remember that there are the remediations posted to help out your quiz or test grade. Something that will also pop up now is there is a homework replacement. So it's literally named Homework Replacement Gas Laws. That you can complete on your own. It's kind of like an independent study. I did post my gas laws videos from last year that kind of go through the different gas laws, the different calculations. That's something you can do on your own. It is math-based, but it's all formulas. So you plug in, solve for X. If you complete that and turn it in, whatever grade you get on it, which hopefully will be 100, that can replace your lowest test grade. So if you completely bombed a homework or you turned it in late and got a 50 and you want to try to get up to 100, you can do that assignment to replace that lowest homework grade. That is set to be due next Wednesday, the 26th, which is that fourth period exam day. That's kind of the last day to turn anything in for you guys. Because we have to have grades submitted next week for you guys that have teacher-made exams. So I'm going to hopefully be submitting grades pretty much next Thursday once everybody takes their exam and it's in. We will take the exam during class. I know Miss Kincaid's class has the exam fourth period on Wednesday. My guys, you have it on Monday. So what we'll kind of do with those extra days next week, because we'll be done with this presentation tomorrow, is that's your time. If you owe me work, you can get that done and taken care of. If you want to work on the homework replacement or remediation, you'll have that time. If you have everything done and you need a brain break, that's kind of up to you on those days that you're not taking your exam. But we're kind of winding down, finishing up. So I'm going to let my guys at home go. I'll stay logged on in case there's any questions. like I said, if you're working on the review, the answers are up. Go through, check them. Don't come up on the exam day that you have no idea how to do stoichiometry. I can't help you at that point in time. But we are going to take the exam during class, but that's so that if you don't understand what a question's asking for, you kind of have access to me and I may be able to lead you in the right direction. So that will kind of be an advantage to you. Remember, the exam is not really a final exam like it has been in the past because it's a teacher-made exam. It's more of just a cumulative test. So it averages in with your test grades, and you're not going to see anything listed in the like final exam category. So that will kind of come up for you guys. So my guys at home, you're welcome to log off if needed. I'll stay logged on if you have any questions.